now that you have a basic understanding of valence bond theory and more importantly molecular orbital theory, we can look into different and more complex structures such as octahedral inorganic complexes. So just to contrast, if we look at two atomic orbitals of a simple diatomic molecule such as hydrogen, we look at a linear combination of atomic orbitals, okay? So LCAOs, that's what we looked at. And so that's of course simple because it just looks at two s orbitals and their interaction. We have anti-bonding and bonding. But for a more complex system such as an octahedral field where we have 6 ligands, we're going to look at what is referred to as ligand field theory, actually not crystal field, ligand field. We'll look at crystal field as well. It's more basic. Ligand field theory is actually more in depth and it builds upon the principles of molecular orbital theory. So instead of looking at just two atomic orbitals and their overlap, we're going to look at all of the ligand metal orbitals, okay, and all of the central atom, the transition metals. So we're going to look at the s orbitals, the d orbitals, the p orbitals, and then all of the interactions of the ligands. And so those are recurred to as symmetry adapted linear combinations. So instead of LCAOs, we look at SALCs. So, but I don't want to complicate things. We can simplify this, and all we have to do is we have to look at you can look at the d orbitals of the geometry that you're interested in, let's say octahedral, and then imagine the ligand coming in, for example, on these axes here, and if you have interaction of the ligand, if the ligand and the orbital here directly overlap, there's a strong perturbation and you see an increase in energy for that, right? So in this case, the dx squared minus y squared and the dz squared for an octahedral geometry would be the two orbitals that are pushed up the highest, right? They have the strongest interaction. It turns out they are degenerate, so they go up in energy equal amounts. And then the other three are actually non-bonding, okay? So you see they come in between, and so there's little to no interaction, and so those are non-bonding. And so the way this octahedral field splits is into 3 non-bonding and 2 bonding orbitals here, right? Which is the dz squared and the x squared minus y squared. So this happens to be where the final electrons are going to be situated, right? So whether you have a d8 or a d1 system, you'll have electrons that are here, and then electronic transitions as well as spectroscopy depends on the size of this gap and how many electrons are there, and their magnetism as well, unpaired electrons or paired electrons. Of course, it gets more complex, but before I move on, I just want to highlight that the designation of these d orbitals is not that complex. You should probably know what they are. So the x squared minus y squared and the dz squared are the ones that are directly on the xyz coordinate system. So x squared minus y squared implies on the x and the y axes directly overlapping. So that's that one butterfly. Everything else also is of course a butterfly if you wish. And then the remaining axis has the dz squared, and that's the one that has that donut in the center. So that's the only thing that's a little odd, but so there's always 2 regions for a d orbital. The others are all in between, so it's pretty simple, right? There's the xy, the xz, and the yz, and that always means it's in between the x and the y axis. The xy, the orbitals are in between. So that's a good thing to know. And so once again, if we're looking at the octahedral geometry, we can clearly see that the ligand orbitals would interact with the x squared minus y squared and the dz squared the most, and then those would be non-bonding, which gives rise to a ligand field splitting diagram that looks like this. Of course, there's more to it because we also have s orbitals and p orbitals. And as I said, we're going to look at symmetry adapted linear combinations. And so this would be the entire picture for the ligand field picture of an octahedral, a generic octahedral complex. So here highlighted in yellow in the center is of course what we just drew. We just derived the 3 non-bonding on top of each other, so they're degenerate. And then these actually, if these look familiar, EG and T2G, those respond to, of course, point group theory, or where they refer to certain symmetries of the interactive ligand and metal orbitals, right? So here we have all of the orbitals for the metal on the left, and here are all of the interactions of the ligands. And so just like MO theory, if we have an A1G that goes down, there's an A1G that goes up, right? And so that still is true. Here are pictures of all of the symmetry adapted linear combinations for each of the transition metal orbitals, as well as the ligand symmetries here, right? So we are well familiar, of course, with what the p orbitals look like and the s orbitals look like. So this is the transition metal, and then here are the transition metal d orbitals. We just looked at those and their designations, and here you have the corresponding ligand points, right? So they're also labeled here, the A1G and the T1G, right? Triply degenerate, right? You can see how they are equivalent. They all have the same shape, but they are in a different orientation that makes them triply degenerate. They interact in the same fashion with your octahedral field. But the bottom line, again, I'm going to go back, is that we were able to predict what the d orbitals do, and this is where the electrons are going to go. So we have the 3 non-bonding, so we have the EG and the T2G, and this is where, again, all of your electronic transitions take place. We can determine our spectroscopy as well as the band gap, blah, 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 blah. Okay, now what about the tetrahedral geometry? That one is a tough one to predict, but it's the opposite here, right? So this splits. We have the dz squared and the x squared minus y squared that are non-bonding, and the other 3 are bonding. So a good way to, so ignore that it says square planar. A good way to imagine this, it's basically just the opposite if it is tetrahedral. Okay, so again, this is just, and it gets different symmetry designations. It's not T2G because the G refers to an inversion center. We know a tetrahedral doesn't have an inversion center, right? So once again, point group theory comes back and haunts you just when you thought you got away from it. All right, so let's think about that. Is easier to predict for us. We think about a square planar geometry. We can most definitely see where the x squared minus y squared would go up the highest, right? That would be a single one that goes up the highest. So then you have 2 that are probably not at all interacting with it, right? So if you have ligands coming in here and here, the dxz and the dyz, that's probably going to be the lowest in energy, or the non-bonding here. So this could be the lowest one here, non-bonding maybe, and then we have these 2 left. They're a little bit harder to predict. You might say this is non-bonding, but there actually is a little bit of perturbation happening here. And the same is true here. We have that donut, so the donut is interacting. So it turns out that a square planar geometry, it's actually that the xy goes up the second highest. So this one actually interacts. This would be the second one. This would be the third one, and then these 2 are non-bonding, if that makes any sense. So this is what the square planar splitting diagram would look like. Again, we have our symmetry symbols here, which you don't have to worry about, but you might want to know how this splits and understand why it splits in this fashion. If you put the square planar and the tetrahedral side by side and look at a D8 complex, right? So this goes back to me talking about that nickel, platinum, and palladium, or any D8 4-coordinate complexes have the tendency or prefer to be square planar, so they would have this geometry, and that for nickel, or if you have very bulky ligands, nickel is the one that can actually go tetrahedral. We had that isomerism We also knew that our electronic transitions were different, right? So the square planar ones were reddish, these were green, greenish blue, and these were red or yellow. So by color we could tell. So of course this refers to the electronic transitions that can take place. But more importantly, if you look at the orbital that needs to be occupied here, right? So we have the dz squared orbital that has electrons in it, and so that explains why we have square planar, because it is filled. And then we have the geometry overlap. It's the dz squared. It's that has to be, actually it's this empty orbital that needs to drop drastically in energy. And it turns out that for platinum and palladium, the energy of the x squared minus y squared is just too high, so it cannot be populated, right? So it makes sense you have to promote electrons in here in order to get it to convert to tetrahedral. And so it just doesn't, it's not possible for platinum and palladium to do that. Okay, just a little side note. Now we're going to look at crystal field theory, which is more simple. Instead of looking at symmetry adapted linear combinations, we're just looking at point charges and looking at the octahedral fields. So the argument made here is that we still have the same pattern. We have the 3 non-bonding orbitals, but instead of them not changing energy at all, they lower a little bit in energy. And the EG, which is of course x squared minus y squared, and the dz squared, they go up in energy, and so you end up with this gap here. And so every electron that is going down in energy into the T to G contributes to 5th, or 0.4 out of 5. And each electron that goes up in energy contributes a 0.6 or 3/5 energy. Okay, and so we can actually then calculate the crystal field stabilization energy by taking the energy of the electrons that are lower in energy and then minus the electrons that go up in energy. So there is a formula that we will look at a little later on, but first of all, there are some factors that can make this gap larger. Because the splitting can differ in intensity, it leads to 2 different scenarios. One where you have a small or weak field where the interactions of the ligands and the transition metal are weak, and this gap is small. It leads to a weak field, which also causes high spin. So what that means is that the electrons that are distributed into these new split orbitals, they spread out as if there is no difference in energy. So the energy difference between these two is not large enough to cause the electrons to pair up before they go to the next higher energy level, right? And so this, in this case of the 4 electrons, leads to 4 unpaired electrons. So that's why this is referred to as high spin. So the more unpaired electrons you have, the higher the spin. And if the gap was large, and they pair up first, then that 4th electron here would pair up, just following Hund's rule, spreading them out and then pairing them up. Again, the energy is too high, and so this would have 2 unpaired electrons, and so this would be a low spin. So here is an example just of a D5 system. It's a little cleaner, where we have low spin and high spin. So strong field is associated with low spin, and weak field is associated with high spin, right? Again, we have high spin, we have a small energy, and the electrons are just as if they were never split. And then, of course, we can have scenarios like this, where here this is a D5 system. All of the energy transitions take place this way, between the T to G and the E to G. EG, there's no T there, it's the T is the triply degenerate part. And so, as you know, if energy is absorbed, the electron can be promoted to a higher level, and then when the electron goes back down, we have energy release, and so we get this electromagnetic spectrum, right? So this is a photon that's not ejected, but releases energy, and so we have 2 components. We have the wavelength and we have the frequency. which is measured in per second. This is measured in meters, and we also know that the speed of light is equal to the product of the wavelength and the frequency. And so the higher the frequency, the shorter the wavelength, right? If you have a short wavelength, you have higher energy as well. So energy is related to this. I have a summary slide here. So these are just formulas. I don't need you to be able to use them, but just as a reminder, we can calculate the energy of a photon based on the frequency of light that we measure. And of course, that's important for our spectroscopy. If we can measure the energy signature of the transition metal complex, then we can make conclusions about its structure and its energy. And so that can be quite important. All right, so, and of course, we have the visible spectrum. We can measure in near red, infrared, we can ultraviolet, and so we can measure outside of the visible spectrum. So even if your transitions are not visible to the eye, we can still measure them. But that's just a little side note. So let's take a look at an example and see what that means for color or energy transitions, right? So here we have two D1 complexes, right? Titanium here is +3. These are neutral ligands, so this means it's D1. So 1 electron, and rhenium-6 as well is also a D1 system. So they both have the same number of electrons, but one is purple, so the titanium one is purple, and the rhenium one is colorless. So that means two things, or one or the other thing, right? The rhenium is either the gap is too small or it's too large, right? So where the energy is either too large and it has a very short wavelength, or the energy is too small, it has a very long wavelength. That causes a, right? So go back to here. If your energy, if you can't see it, that means it's going to be less than 300 nanometers, and so it's going to be higher in energy. It's going to be in the ultraviolet region, or if it's if the gap is larger than 750 nanometers, then we have a low energy, and so this would be a smaller gap. So which one is it in this case? All right, so the titanium falls right in. It's purple, falls right in there, and this one has a short wavelength, which means it's too high in energy, so the gap for the rhenium is too large. So that means it's either the ligands that are causing that, or maybe the metal, or so what is it that causes that gap to be larger or smaller? They both have the same number of ligands, so that's also important. So let's go through each of the different factors that affect this gap, right? So oxidation number makes a lot of sense, right? So here we have cobalt 1. These are neutral ligands, and here's cobalt 3, right? The ligands can go in deeper if you have a higher charge, right? Because you're removing electrons from the center. So you're going to have a larger gap for the higher oxidation number. So that makes sense, right? So that causes that gap, and the ligands to go in deeper, splitting that distance between the EG and the T2G even higher. The nature of the metal ion, okay? So 3D is larger than 4D, is larger than or equal to 5D, okay? So and that has to do with electron shells, right? You get softer and softer the more electron shells you have. And so if you have, so cobalt, these are all in a row, cobalt to rhodium to iridium, we see an increase between 3D and 4D in general, right? So we have more electrons, which means the ligands can go in further, causing a larger gap. And so I have a question mark here. I don't have a number here. It says larger than or equal to, and this goes back to the concept of the lanthanide contraction, where this is going to be right around 410. It's not going to be much larger because of the lanthanide contraction. We actually have more electrons, but we don't have a softer shell. So the 4D and the 5D are going to be pretty similar in splitting. But in general, if you have a larger atomic radius, you have a smaller shell, and therefore your delta naught, as we call it, or your splitting size of the gap is going to be larger. The number of ligands, that also makes sense, so they're harder to compare. But if you have 6 ligands versus 4 ligands, you're going to have a larger gap for the more ligands, right? So that's gonna increase. The nature of the ligand, so I suggest that you have this handy when you take the exams. It's not just important for for this chapter, it's also going to spill over into the next one. So have this, the nature of the ligand here, weak field to strong field ligands. So we have the carbonyl, so those that can do pi back bonding, they are the ones that have the strongest field because they are pi acceptors, right? Pi back bonding. Then we kind of have the weakest ones are going to be the pi donors, so pi donors. And then in the middle we have the sigma donors, but you know, you have access to that, so you don't have to memorize it or anything like that, but just in general. So you can also look at the types of atoms we have here, right? So halides here are in general weaker, and then we have carbon that's interacting here, and then we have the amines and the oxo ligands here. Urea is also nitrogen, and then anyway, not all that important. And finally, easy to answer, easy to test you on, to calculate the crystal field stabilization energy, knowing the field splits like that, and that just knowing the vocabulary, strong field versus low field. And so if you have a system with 4, let's make this 5. If we have 5 and we have a strong field, they go 1, 2, 3, 4, 5, and then we would have 5 electrons that go into here. They each contribute a factor of 0.4 to bonding, and then we subtract 0 minus 0.6, and P is just the pairing energy, and so it's not going to have a value. We're simply going to call this, in this case it's 2P. It's just part of the formula, and so now we have 0.4 times 5, which is of course 2.0 minus 0, so that would be 2.0 minus P would be this crystal field stabilization energy for the system. So I might ask you to calculate the crystal field stabilization energy for any of these systems, or I may give you a compound which is a little bit more complicated because you have to figure out the D system, and then you might have to consider, is it going to be a strong field or a weak field based on the factors that we just went through. But let me just give an example. So if we have high spin D7, we have 1, 2, 3, 4, 5 d orbitals. There are 7 electrons. 1, 2, 3, 4, 5, 6, 7. We know high spin means we have a weak field, so I'm going to try to have that gap pretty small. Okay, and then I will spread out the electrons 1, 2, 3, 4, 5, as if there was no energy difference. If it was low spin, then we would draw the gap larger, and then 1 electron would be down where the T2G is. But now that we have the splitting diagram, we can then calculate 5 times 0.5 minus 2 times 0.6, right? Each of these gets 0.6, each of these gets 0.4. This is 2.0, this is 1.2, so that gives me 0.8, and then we have the pairing energy, which is 2 paired up minus 2p. Okay, so I'm not going to do the other 3. You can do this yourself, and then this is actually always the same. So here's your answer to any of them, right? So you can do the weak field D8. So weak field D8, here's your answer, is going to be 1.2 minus 3p, so you can verify any of those and do them yourselves. And so this is enough. I've had enough, and we're moving on to kinetics.